Charges on a string. Charges on a string, and this is cool because we're combining some dynamics here with electricity. We have two identical charged spheres, A and B, with a mass of 0.62 grams. They're suspended from two strings as shown. The spheres carry equal charges, minus 12 nanocoulombs, and are separated by a distance of 2.5 meters. So here's the string hanging from the ceiling probably. Here's a charge object. Here's another string. Here's another charged object. Draw a free body diagram showing all forces applied on sphere B. Find the tension force in the lower string, F slant T2. Draw a free body diagram and show all the forces applied on sphere A. Find the tension force in the upper string, F sub T1. Draw a free body diagram showing all forces applied on sphere B. B has a mass, bang, so there's mg. That's always a given. The masses are equal, so we don't have to use subscripts here. We don't have to show m sub bg or m sub ag, just put mg. The string comes out of the top of B, so the tension, Ft2, is in the up direction. Since the charges are both negative, they repel each other, so the electric force will be down. Notice we don't put in F sub T1 for object B. Why? It's not touching it. These are contact forces. If Ft1 doesn't touch B, it doesn't get to be part of its free body diagram. And what's the acceleration here? Nothing's moving, so the acceleration is 0. Find the tension force in the lower string. We use Newton's second law, F equals ma. And what forces do we have? We have F sub T2 in the up direction. We have the electric force in the down direction. And we have mg in the down direction. The acceleration is 0, so this term is just going to be 0. We then solve for F sub T2. We move F sub E, the electric force, and mg to the right side. And then we substitute in Coulomb's law for the electric force. And what more can we do here? Oh, the charges are the same, right? So instead of QA and QB, that's just equal to Q squared. We don't even need the subscripts there. And now it's just a matter of plugging in the correct variables. So what's the trick here? Well, we have to make sure we're in coulombs. Okay, so what are the charges with nanocoulombs? So you multiply the nanocoulomb by 10 to the minus 9th, and you get coulombs. And kilograms, did we have to do anything there? Yep, because we were given grams, right? It was 0.62 grams. So you have to move the decimal place 3 to the right to get kilograms. So that's 6.2 times 10 to the minus 4th kilograms, which we plug in here. And here's our gravitational acceleration. We add those two values together, and it's kind of a yucky calculation, but here you go. Tension force is 0.00815 newtons. Time for the free body diagram for sphere A, this guy up here. So A has a mass. There's mg. Okay, masses are equal, so we can just put mg. We don't need a subscript. A string comes out the top of A, so the tension in that string, Ft1, points upwards. Okay, good. Another string comes out the bottom, so we have Ft2. The charges are both negative, so they repel, which means the electric force vector is in the up direction. And once again, the acceleration is 0 because nobody's moving. We use Newton's second law. Sum of the forces is ma. So who's pointing in the up direction? Well, T1 over here, and the electric force. Who's in the down direction? Well, we have T2, so that gets a negative sign. And mg, also a negative sign. And that equals ma. ma is 0. So we isolate the tension force in the first string. It's Ft2 plus mg minus the electric force. And then what is the electric force? We use Coulomb's law, kqqq over r squared. And both charges are the same, so we do the same trick. We get kq squared over r. And now it's plug and chug. I feel if you get this far, this should give you most, like 90% of the credit here. There's the physics. Now you're just putting numbers in. So we have T2. Where did we get that? We got that from the earlier problem, okay? That was not a given. We calculated that. Here's the mass of the sphere, g. Here's the charge, And since it was given in nanocoulombs, you multiply it by what? 10 to the minus 9. And then your mass was 0.62 grams, which we converted to 6.2 times 10 to the minus 4 kilograms. And the distance between these two spheres was 2.5 centimeters. You move the decimal 2 to the left to get meters, and that's 0.025 meters. So you add all this, subtract all this, and you get the tension force in the top string is 0.0122 newtons. All right, there's a much more fun and intuitive way to solve this problem. We derive these equations in parts D and B, right? Tension 1 is tension 2 plus mg minus kq squared over r squared. And then here's our tension force in T2. And we got these from the Newton's second law equations based on the free body diagrams. How about, look at this. Look at f of T2 here, f of T2 here. This equation has a positive kq squared over r squared. This one has a negative. Can you see where we're going with this? We're going to substitute this expression into this one. So we have the tension force in one is kq squared over r squared plus mg minus kq squared over r squared. Okay, because why did that happen? Well, T2, this is our T2, and here was the rest of the equation from T1. Okay, and look at this. This goes out. We didn't have to do all that messy calculation. So tension 1 is equal to mg plus mg. Tension 1 is twice mg. It does not depend on the electric force at all.